In the previous lectures, we discussed about the exact algorithm using solvers to get the solution for TSP or VRP. However, when we use mixed integer programming, the solution is exact, but the problem scale is relatively small we can handle. However, in reality, sometimes we need to address a large-scale TSP instance. We need to develop fast algorithm, which will be provided in this lecture. In particular, we will focus on greedy algorithm and a meta-heuristic algorithm. So both of these two algorithms today we discuss, they provide an estimation of the solution. So their solution is approximated, and then they can handle very large scale. Okay, so let's start from the greedy algorithm. In particular, for TSP problem, we will have the simple and famous greedy algorithm we call true opt. This opt indicates optimization. So the idea behind the true opt algorithm is very simple. For example, if we have 4 points, our intuition tells us we should go in a tour like this. So if you find out a tour which is like this, then definitely we know this is good and then this is not good. So when we tell some TSP solution, one can immediately tell that a solution is not optimal because you see the crossing. So this is very simple to prove that a TSP tour with crossing is not optimal because we can easily connect this line and then this line because the summation of two edges is greater than one edge for a triangle. So the new TSP tour will have smaller distance. Okay, so how can we guarantee that there is no crossing? One easy way we can tell is that if we have A, B, C, D, in this case, we can have some other nodes. So let's discuss about how can we guarantee that the solution has no crossing. Consider that we have a TSP tour with crossing. So let's denote the 4 nodes related to the crossing as A, B, C, D. So this original TSP tour contains many points, but definitely we see a crossing. So we can write this TSP tour as A to B, and then B to some nodes, and go to C, C to D, and then D go to some nodes, and then go back to A. So if we see a TSP tour with this crossing, we can easily reduce its distance by what we just showed using the properties of a triangle. So in this case, we can have A to C and then B to D. But we should also know that the direction previously is A to B and then B to C, so the direction is in this way. But now after we remove the crossing, the direction from A to C and then C to B, and then B to D, D to A. So after we change this, we have A to C, and then C to B, B to D, and D to... And know that from C to B, this is a path that reverse the previous path B to C. For example, if previously we have B, E1, E2, E3 to C, now we will have C to E3, E2, and then E1 to B. So after we remove this crossing, we can definitely reduce the distance. So to really implement this algorithm, we can just find out any 4 points from a subset, let's see, A, B, C, D. If we can find the distance from C, A, B, so the total TSP tour previously is the edge, the distance from A to B plus the distance of path B to C, and then plus the distance from C to D, and then plus the path from D to A. After we do the swapping, then our new structure will be A to C, E to D. So the total distance will be A to C plus the path from C to B plus the edge B to D plus the path D to A. So interestingly, we find out that when we reverse the path from B to C to C to B, their total distance should not change. And then the path from D to A is the same. So the only difference will be the summation of the distance from A to B and the distance from C to D, pairing with those where we have the summation of distance from A to C and then the distance from B to D. So in this sense, if we can have CAB plus CCD is greater than CAC plus CBD, then we know that we can do the swap. So we try to enumerate all possible 4 nodes pairs, 4 nodes subsets, and then we can guarantee that. Okay, so then for any given initial TSP tour, we can always enumerate all possible A, B, C, D. Each of this point is selecting from all the node sets, and then we will check each pair, and we will check each of them to see if there's a chance we can reduce the cost. So if exist is greater than, then we do the swap until finally we cannot improve. So this is our 2-opt algorithm, which is pretty simple.